Now let's talk about limits. We have here an introduction about limits. As you remember, we discussed the algebra and pre-algebra briefly before we get into the calculus so that you guys are ready and not shocked about the new concept that you're having. What I would like you to know is that the limits is the smallest introduction to integration and differentiation. So for now, we will talk a little bit about the limits as a brief introduction. What is limits and how does it work, and all the concepts that are around limits. Let's get into our presentation. So if we want to do a non-formal definition for the limit, so the limit of a function, if that function exists for some x value c, is the height the function gets closer and closer to as x gets closer and closer to c, either from left or from right. If that doesn't make sense, that's totally normal. Let's have our pointer in here. So looking at the Cartesian here, we have the y-axis in here with the grades on it from 1 to 9, and we have the x-axis in here with the grades from 1 to 4. This line representing f of x equal 3x plus 1, you already learned that in high school, how to draw that kind of line. Let's say that the line is already there in the Cartesian. F of x equals 3x plus 1. So you are saying as x approaches to 2, f of x approaches to 7. Either he approaches from the left or from the right. As x approaches to 2, f of x approaches to 7. So if we have a table for that, as x equal 1, f of x in this case would equal 4 at the point where it having a cross section with the f of x equal 3x plus 1. As it is going to 1.5, it's 5.5 for f of x, 1.999, it's 6.999. That's approaching from the left. So as you are approaching x from the left, which means you're going from this way to the right, and you're approaching as well from the right to the same point and giving your values as an output. So as you're approaching 2, like x is approaching to 2 from the right, when your x equals 3, then your f of x equals somewhere here 10. When your x equals 2.01, which is somewhere here, then your f of x equals 7.03. To understand more in an interactive way, let's jump into our sketch. So here I generated f of x equal 3x plus 1. On the right you can see the graph for the f of x plus 1 on the Cartesian. We have the y-axis that we talked about, and we have the x-axis over here. Now you're approaching, while you're approaching, you don't approach exactly on the x-axis or on the y-axis. You're approaching by following the line of the function or the curve of the function, whatever function you're using. So here, let's see. Now the program here is giving us the x and y points as we're moving on the graph. So I drawn the graph of 3x plus 1, that's in purple. Then now as x equal 0.06, y, which is f of x, the function we have right there, equals 1.17. Remember, this is the 2 here. So we're approaching from the left to the 2. As you're approaching x, you have a relative y value, which is the f of x. So as x equal 1.23, y is going to be 4.68. You are getting closer and closer, as we saw in the table, to the value of 2. As x equal 1.81, y equals 6.42. So we're approaching to the value of 7 for the f of x, or the y in this case. Let's keep going. As x approaches to 2, at this point x is exactly 2, then f of x is exactly 7. But since we're talking limits, there's nothing exact in here. Otherwise, you could say if f of x equals 3x plus 1, f of 2 equals 7, as easy as that. But in many cases, as we learn, as we move forward, limits are useful because some of those functions are not continuous. It's not like one straight line like here. You can have a couple of lines and couple of functions represented on the graph that you want to try to approach from left or right to find the closest solution possible to the reality. So I hope that identify what limits are. So you're approaching from the left. If you approach from the right, which is from here all the way to the y, to the 2, I mean. So you go, when your x is equal 2.22, then your f of x is 7.66. When your x is 2.15, f of x is 7.46, and so on. Let's go back to our presentation. So you can see here in the table, he captured when x equal this, f of x equal that, as he's moving over to the graph over here for the function. Now, it's important to know that there's a couple of types for the limits. The limits, either the regular or the one-sided. Regular, that's the two-sided one, the one that's pretty famous and everybody know. And there's the one-sided limit. What's the difference? Two-sided limit, when you have a certain point on the graph that you want to approach from the right or from the left, like x approaching to 2 in this case from the left, you can see this arrow approaching to that point, and x approaching from the right, then you're approaching to 2 as much as you can on the graph of the function g of x in this case. If you have a one-sided limit, then you have this function being represented in here, then you are approaching the point in here only from the right. You can see there's a graph here and there's a graph here. Then you need to approach that exact point from the right only or from the left only. We will learn when is the case that you can only approach the limit from one side, and we learn more about it. Now, if we want to go to the formal definition of the limit, formal definitions say let function f be a function and c a real number. Then the limit as x approaches to c, if you see here x arrow c, we're saying lim as the limit, so you read it limit as x approaches to c of f of x, or some people say limit of f of x as x approaches to c. Now we are interested in knowing if that limit exists or doesn't exist. How to test the existence of a certain limit? Then limit the f of x as x approaches to c exists if and only if, which you can say exists only if one of those conditions or all of those conditions apply based on the equation. So here we say limit f of x as x approaches to c minus, what does it mean? It means as x approaches to c from the left, it should be exist. Then as limit of f of x as x approaches to c from the right exist, and as well the limit f of x as x approaches to c from the left equal the limit f of x as x approaches to c from the right. So if you see a plus sign means x approaches c from the right. So it's important to know that limit exists. If you say the limit is exist, that means the limit equal a finite number, an actual number. In this case, we say the limit exists. If the limit doesn't equal an actual number or a finite number, then we say the limit does not exist. Now, if we want to look closer to one-sided limit, so you have two graphs in here represented in a certain way. We will be familiar more with those graphs in the future, having those empty and full circles. So one-sided limit, it will be in this shape. Limit p of x, which is a function, doesn't matter, f of x, p of x, g of x, the same, as x approaches to 3 from the left equals 6. That's a one-sided limit. In specific, a left-sided limit, if you want to be accurate. Then there's the limit of p of x, where x approaches to 3 from the right equals 2. That's a one-sided limit, in specific, a right-sided limit. If we look at the graph, what does it mean with those? So limit p of x, assuming this is a p of x in here, as x approaches to 3 from the left. So we're going on the graph. We said we can't go freely. We are following the graph. We're approaching the 3. Here's the 3 from the left. That's the left side of the 3 or of the x-axis. As we approach, then we are getting closer to C. If you generate a table as the one we saw, that means we're getting closer to the number 6 in here. Then the limit of p of x as x approaches to 3 from the right. Let's say this function is made out of 2 pieces because it's a discontinuous function, but it is exactly the same function. But we're approaching the 3 from the right. So limit p of x as x approaches 3 from the right. As you're getting closer to 3 following the graph, then you are getting the f of x closer to number 2.